Right now, as you sit there, the only thing keeping you alive is a thin blanket of air pressing against every inch of your body. You don't feel it. You never think about it. But if you were suddenly transported into space, no asteroid would need to strike you, no alien weapon would need to fire, nothing would need to touch you at all, and yet your body would begin to die within seconds. Your blood would start to bubble, your lungs would rupture from the inside. Radiation invisible to your eyes would begin shredding your DNA strand by strand. Space doesn't need claws or fire or impact. It kills with absence. It kills with invisible forces that pass through walls, through skin, through bone. And tonight, we're going to understand exactly how. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Let's start with something you do every single second of your life without ever thinking about it. You exist under pressure. Right now, as you sit there, the atmosphere above you is pressing down on every square inch of your body with a force of about 14.7 pounds. That doesn't sound like much until you realize how many square inches your body has. The average adult human body has a surface area of roughly 2,700 square inches. Multiply that by 14.7 pounds per square inch, and you get somewhere around 40,000 pounds of force pressing against you at all times. That is roughly the weight of 4 adult elephants distributed evenly across every part of your skin. You don't feel it. You have never felt it. And the reason you don't feel it is because the pressure inside your body pushing outward matches the pressure outside your body pushing inward. Your blood, your tissues, your organs, your fluids, everything inside you exists in equilibrium with the atmosphere around you. The air presses in and your body presses out, and these two forces balance each other perfectly. You are, in a very real sense, a pressurized container. Your body is engineered by evolution to function at this specific pressure. Every biological process that keeps you alive, from the way oxygen binds to hemoglobin in your blood, to the way fluids move through your tissues, to the way your lungs inflate and deflate, all of it depends on this pressure being present and constant. Your body doesn't just tolerate atmospheric pressure, it requires it. It was built for it over hundreds of millions of years of evolution, every generation living and dying under this same invisible ocean of air. Now, take that pressure away. This is what space does. Space is a vacuum. Not a perfect vacuum, technically. There are a few atoms per cubic meter in interstellar space, mostly hydrogen. But for all practical purposes, the pressure in space is zero. There is no air. There is no atmosphere. There is nothing pushing against you from the outside. And the moment you are exposed to that nothingness, everything changes, because suddenly, the pressure inside your body has nothing to push against. The equilibrium that has kept you alive every second of your existence is gone. And your body, which was designed for one very specific environment, it is now in an environment it was never meant to experience. What happens next is not what most people think. Movies and science fiction have given us a dramatic but mostly wrong picture of what vacuum exposure does to the human body. In some films, people explode. Their bodies burst outward like overinflated balloons. In others, they freeze instantly, their skin turning blue, ice crystals forming on their face within seconds. Neither of these things actually happens. The reality is different. In some ways, less dramatic than fiction, but in other ways, far more disturbing, because what actually happens is quiet, internal, and almost invisible from the outside. Your body does not explode in a vacuum. Human skin and tissue are remarkably strong. Think about it. Your skin holds together just fine under normal conditions, even when you're bruised or cut. It's flexible, elastic, and tough. The pressure difference between the inside of your body and the vacuum of space, while significant, is not nearly enough to tear human tissue apart. 14.7 pounds per square inch is a lot of force when distributed over your whole body, but it's not enough to rupture skin. If you inflated a balloon to 14.7 pounds per square inch, it wouldn't pop. Your body is much stronger than a balloon. So no, you would not explode, but you would swell. The gases dissolved in your body fluids and tissues would begin to expand. Your body would puff up, perhaps to roughly twice its normal size. Not because it's tearing apart, but because the gases inside have nothing holding them in anymore. Think of it like this. When you open a bottle of soda, the carbon dioxide that was dissolved under pressure suddenly has room to expand. It fizzes and bubbles. Something similar would happen inside your body. The nitrogen and other gases dissolved in your blood and tissues would begin to come out of solution, forming bubbles. This process is called ebulism, and it is one of the most dangerous immediate effects of vacuum exposure. Ebulism is related to something scuba divers already know about: decompression sickness, commonly called the bends. When a scuba diver ascends too quickly from deep water, the nitrogen dissolved in their blood under high pressure comes out of solution and forms bubbles. These bubbles can block blood vessels, cause extreme pain in joints, and in severe cases, be fatal. Decompression sickness happens when you go from high pressure to normal pressure too quickly. Ebulism is what happens when you go from normal pressure to essentially no pressure. It is decompression sickness taken to its absolute extreme. The bubbles don't just form in your blood, they form everywhere. In your muscles, in your organs, in the fluid around your joints, in the tissues of your brain. And these bubbles expand because there's no external pressure to keep them small. Your circulatory system, the network of blood vessels that carries oxygen and nutrients to every cell in your body, begins to fail. The heart is still beating, still trying to pump blood, but the blood is now full of gas bubbles. The heart can't pump foam effectively. Blood flow to your organs begins to drop. Your brain, which is extraordinarily sensitive to oxygen deprivation, begins to shut down. You have roughly 15 seconds of useful consciousness. 15 seconds. That's not a guess or an estimate. We know this because of an incident that happened on December 14th, 1966, at the Manned Spacecraft Center in Houston, Texas, which later became the Johnson Space Center. A technician named Jim LeBlanc was testing a spacesuit in a vacuum chamber. The pressure in the chamber was reduced to simulate the conditions of space. During the test, the hose supplying pressurized air to his suit disconnected. LeBlanc was suddenly exposed to a near vacuum. Within seconds, he felt the saliva on his tongue begin to boil. Not because it was hot, but because the boiling point of a liquid decreases as pressure drops. At sea level, water boils at 212 degrees Fahrenheit, but at very low pressures, water can boil at body temperature or even below it. The moisture on LeBlanc's tongue and in his mouth began to bubble and vaporize. He lost consciousness in about 14 seconds. Fortunately, the chamber was repressurized within about 25 to 30 seconds, and LeBlanc recovered fully. He later reported that the last thing he remembered was the sensation of the water on his tongue boiling. This incident is one of the few real data points we have about what happens to a human in a near vacuum, and it confirms several important things. First, you don't explode. LeBlanc's body stayed intact. Second, you don't freeze instantly. The exposure lasted roughly half a minute, and temperature was not the immediate danger. Third, you lose consciousness very quickly, about 14 to 15 seconds. And fourth, if repressurization happens within about 60 to 90 seconds, survival is possible. Beyond that window, the chances drop rapidly. Let's talk about your lungs, because this is where one of the most counterintuitive dangers lies. If you are suddenly exposed to vacuum, your first instinct would probably be to hold your breath. This seems logical. You're about to be in an environment with no air, so you should hold onto the air you have, right? Wrong. Holding your breath in a vacuum is one of the worst things you could do. Your lungs are essentially thin-walled bags filled with air. Under normal atmospheric pressure, the air inside your lungs and the air outside your body are at the same pressure. But if the external pressure suddenly drops to zero and you're holding your breath, the air inside your lungs will expand rapidly, and your lungs cannot stretch enough to accommodate it. The result is pulmonary barotrauma. Your lung tissue tears. Air escapes from the lungs into the chest cavity and potentially into the bloodstream itself, causing air embolisms that can travel to the brain and cause a stroke. The correct thing to do is to exhale. Let the air out as quickly as possible. You'll lose your air supply, but your lungs will remain intact, giving you a chance of survival if you can be repressurized quickly. Now, let's talk about what happens to the rest of your body in those critical first seconds and minutes. We've covered embolism and lung damage, but there's more. Without atmospheric pressure, the boiling point of water drops dramatically. At the pressure of space, essentially zero, water boils at temperatures well below normal body temperature. Your body is roughly 60% water. The water in your tissues, your blood, your saliva, the moisture on the surface of your eyes, all of it would begin to vaporize. This doesn't mean you would instantly dry out like a mummy. The process takes time because the heat required to vaporize water, called the latent heat of vaporization, has to come from somewhere. It comes from your body. As water evaporates from your skin and mucous membranes, it actually cools the surrounding tissue. This is the same principle that makes sweating work on Earth. Evaporation removes heat. In a vacuum, this evaporative cooling would cause the surface of your skin and the membranes of your eyes and mouth to cool rapidly, potentially leading to localized frostbite. But the cooling is the surface effect. The interior of your body would remain warm for a while because human tissue is actually a decent insulator. Your core temperature wouldn't drop dramatically in the first minute or two, so you wouldn't freeze to death, at least not quickly. The immediate dangers are all about pressure, not temperature. The loss of consciousness happens because of oxygen deprivation. When the pressure drops, the oxygen in your lungs can no longer be transferred to your blood effectively. In fact, the process reverses. Oxygen begins to move from your blood back into your lungs and then out into the vacuum. This is because gas exchange in the lungs is driven by pressure gradients. Normally, the partial pressure of oxygen in the air in your lungs is higher than the partial pressure of oxygen in your blood. So oxygen moves from the lungs into the blood. In a vacuum, the partial pressure of oxygen in your lungs drops to zero. So oxygen moves the other way, from your blood into your empty lungs and then out into space. Your blood is being actively stripped of oxygen. Your brain, which consumes about 20% of your body's oxygen, despite being only about 2% of your body weight, is extremely sensitive to oxygen deprivation. Within 4 to 6 seconds of losing your oxygen supply, you begin to feel lightheaded. Within 10 seconds, your vision would start to narrow and darken. By 15 seconds, you'd lose consciousness. Your brain simply cannot function without a continuous supply of oxygen. This timeline is well established. It matches what we know from high-altitude decompression incidents, from the Jim LeBlanc vacuum chamber accident, and from studies of rapid decompression in aircraft. There is one more real-world case that demonstrates the lethality of vacuum exposure, and it's far more tragic than LeBlanc's experience. On June 30th, 1971, the Soviet spacecraft Soyuz 11 was returning to Earth after a successful 23-day mission aboard the Salyut 1 space station. The crew consisted of 3 cosmonauts: Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev. They had just completed the longest spaceflight in history at that time. During the separation of the descent module from the orbital module, a pressure equalization valve opened prematurely. This valve was designed to open only after landing to equalize cabin pressure with the outside atmosphere, but it activated during module separation while still in space. This valve, only about the diameter of a small coin, allowed the air inside the capsule to escape into space. The cabin depressurized in roughly 30 to 115 seconds. The cosmonauts were not wearing spacesuits. At the time, Soviet spacecraft were designed so that the crew could fly without suits to save space and weight. The crew would have noticed almost immediately the hissing, the dropping pressure. One of them, Patsayev, was found with his seatbelt unfastened, suggesting he tried to locate and block the leak. But in the rapidly thinning air, there was no time. Within seconds, they would have experienced the same sequence LeBlanc experienced. The boiling of fluids, the drop in blood oxygen, the narrowing of vision, and then unconsciousness. The entire cabin would have reached near vacuum conditions in under 2 minutes. When the capsule landed automatically and the recovery team opened the hatch, they found all 3 cosmonauts dead in their seats. There were no signs of physical trauma, no burns, no impacts, no wounds. They looked like they were sleeping. The vacuum had killed them silently, invisibly, without leaving a mark on their bodies. This is the defining characteristic of death by vacuum. It doesn't look like anything. There's no violence you can see. The body remains outwardly intact. The damage is entirely internal. Gas bubbles in the blood, oxygen stripped from the tissues, cellular damage from within. Space killed them without touching them. After the Soyuz 11 disaster, the Soviet space program made spacesuits mandatory during launch and re-entry. This policy has remained in place ever since for both Russian and American crewed missions. The lesson was learned at the cost of 3 lives. Let's go deeper into the biology of what pressure does for you, because understanding this helps explain why the vacuum of space is so fundamentally hostile. Atmospheric pressure doesn't just keep your body from swelling, it keeps your entire biochemistry functioning. Enzymes, the proteins that catalyze virtually every chemical reaction in your body, are shaped by their environment. They fold into specific 3-dimensional shapes that allow them to do their jobs. Changes in pressure can alter these shapes, disrupting the enzyme's ability to function. Under normal conditions, this isn't an issue because atmospheric pressure is very stable. It fluctuates slightly with weather patterns, but not enough to affect biology. In a vacuum, however, the pressure change is so extreme that proteins and other biological molecules can be affected. Cell membranes, which are essentially thin films of fat molecules, rely on pressure to maintain their structure. In a vacuum, these membranes can become unstable. The gas bubbles forming in and around cells can physically deform and rupture cell membranes, killing cells directly. This is happening throughout your body simultaneously. It's not localized to one area. Every tissue, every organ, every cell is experiencing the same pressure drop at the same time. Your circulatory system is particularly vulnerable. The heart is a pump designed to move liquid blood through a network of vessels. When blood begins to foam, when gas bubbles form throughout the circulatory system, the heart loses its ability to generate effective flow. It's like trying to pump a milkshake through a straw versus trying to pump whipped cream. The foam doesn't flow properly. Blood pressure drops. Organs that depend on constant blood flow, especially the brain and kidneys, begin to fail. The cardiovascular collapse that occurs during vacuum exposure is not like a heart attack. It's not a blockage in one artery. It's a systemic failure of the entire circulatory system as the blood itself becomes unable to function as a transport medium. Every cell in your body needs 3 things to survive: oxygen, nutrients, and the removal of waste products. All 3 of these depend on blood flow. When blood flow fails, cells begin to die. Brain cells die first because they have the highest metabolic rate and the lowest tolerance for oxygen deprivation. Heart muscle cells die next, then kidney cells, liver cells, and so on. The process cascades outward from the most sensitive tissues to the least sensitive. This is why the timeline matters so much. In those first 15 seconds, you lose consciousness as your brain runs out of oxygen. If repressurization happens within roughly 60 seconds, most of the damage is reversible. The gas bubbles can be reabsorbed. The heart can resume normal pumping. The brain, if it hasn't been deprived of oxygen for too long, can recover. But after about 90 seconds, the damage becomes increasingly severe. After 2 minutes, survival becomes unlikely. After 4 to 5 minutes, the cellular damage throughout the body is so extensive that even if you were somehow repressurized and resuscitated, you would likely have permanent brain damage and organ failure. There's also something called water vapor pressure that plays a role. At normal body temperature, 37 degrees Celsius or 98.6 degrees Fahrenheit, water has a vapor pressure of about 47 millimeters of mercury. In a vacuum, where the external pressure is essentially 0, any liquid water at body temperature will boil. This means the water in the thin layer of fluid covering your eyes will boil. The saliva in your mouth will boil. The moisture lining your nasal passages and throat will boil. The sweat on your skin will boil. Again, this boiling is not because the liquid is hot, it's because the pressure is too low for liquid water to exist at that temperature. The boiling point and the body temperature have crossed paths. Liquid water at 37 degrees Celsius simply cannot remain liquid at near 0 pressure. It must become vapor. This is one of the most alien concepts for most people to grasp. We associate boiling with heat. We think of boiling water as something that happens when you put a pot on a stove. But boiling is actually about pressure as much as it is about temperature. At the top of Mount Everest, where atmospheric pressure is only about 1/3 of sea level pressure, water boils at roughly 70 degrees Celsius instead of 100. In space, water boils at temperatures far below what we'd consider cold on Earth. This is why LeBlanc felt his saliva boiling on his tongue. It wasn't hot. It was his body temperature, the same temperature it always was. but the pressure had dropped so low that body temperature was now above the boiling point. All of these effects, the embolism, the lung damage, the oxygen deprivation, the boiling of fluids, the cardiovascular collapse, they all happen because of one thing: the absence of pressure. Space doesn't attack you. It doesn't send something toward you that does damage. It simply removes something you need. It takes away the pressure that your entire biology depends on. And without that pressure, your body destroys itself from within. This is what makes vacuum exposure so conceptually unsettling. There is no enemy. There is no weapon. There is no force striking you. There is only absence. The absence of air. The absence of pressure. The absence of the environment your body was built for. And that absence is lethal. Think about how strange this is. Almost every other danger humans face involves something acting on us. A predator bites you, a falling rock strikes you, fire burns you, a disease infects you. These are all active threats, things that come at you and do damage through contact or interaction. Vacuum is different. Vacuum is the absence of everything. It is nothing. And nothing, it turns out, can kill you. Your body is so precisely adapted to Earth's atmosphere that removing that atmosphere is fatal. Not because something attacks you, but because your body's own internal processes, the very processes that keep you alive, become destructive without the external environment they evolved to work within. Your blood, which carries life-giving oxygen under normal conditions, becomes a foaming mass that clogs your vessels. Your lungs, which exchange gases to keep you breathing, collapse or rupture. The water that makes up most of your body, the solvent in which all your biochemistry takes place, boils away into vapor. Space doesn't kill you. Your own body kills you because it can't handle the absence of the environment it was designed for. This is perhaps the most important concept to understand about why space is dangerous. Space is not actively hostile in the way we usually think of hostile environments. It doesn't have teeth or claws or weapons. It's not trying to kill you. It is simply an environment where the conditions necessary for human life do not exist. And when you place a human body in an environment where the conditions it needs are absent, the body fails. Quickly, quietly, and completely. And the terrifying part is how thin the barrier is between you and that lethal emptiness. The International Space Station, which currently orbits Earth at an altitude of roughly 250 miles, is protected by a hull that is in most places only a few millimeters thick. A few millimeters of aluminum and composite material are all that separate the astronauts inside from the vacuum that would kill them in minutes. The spacesuits astronauts wear during spacewalks are impressive pieces of engineering, but they're essentially sophisticated balloons. They maintain about 4.3 pounds per square inch of pressure inside, which is less than a third of sea level atmospheric pressure. This reduced pressure is enough to keep the body functioning, but it requires astronauts to pre-breathe pure oxygen for hours before a spacewalk to purge nitrogen from their blood and prevent decompression sickness. A puncture in a spacesuit, depending on its size, could be catastrophic. A small hole, say the size of a pinprick, would allow air to leak out slowly. The suit's life support system could compensate for a while by pumping in more oxygen. But a larger hole, even one the size of a pencil tip, could depressurize the suit faster than the life support system can compensate. The astronaut would have minutes or less to get back inside the airlock. Every spacewalk carries this risk. Every moment an astronaut spends outside the station, they are separated from death by a few layers of fabric and a pressure seal. The engineering is remarkable, the safety record is extraordinary, but the fundamental vulnerability never goes away. Humans were not designed for space. We carry our environment with us when we go there, a tiny bubble of Earth's atmosphere wrapped around our bodies. And if that bubble fails, even for a minute, space will kill us with nothing more than its emptiness. Now let's talk about something you cannot see, cannot hear, cannot smell, and cannot feel, but that is streaming through your body right now as you listen to these words. Radiation. On Earth, you are exposed to small amounts of radiation every single day. It comes from the ground beneath your feet, from the food you eat, from the building materials in your home, and from space itself. But the amount that reaches you is tiny. It is filtered, weakened, and deflected by two of the most extraordinary shields in the solar system: Earth's atmosphere and Earth's magnetic field. These two invisible barriers are the reason you are alive. Without them, the radiation environment you experience would not just be uncomfortable, it would be lethal. And in space, beyond the protection of these shields, radiation becomes one of the most insidious dangers any living organism can face. Because radiation does not need to touch you in the way you normally think of touching. It doesn't push, press, or strike in any way your senses can detect. It passes through you, through your skin, through your muscles, through your bones, through the walls of your cells, and into the very molecules that carry your genetic code. And when it gets there, it breaks things. To understand why radiation in space is so dangerous, you first need to understand what radiation actually is. The word radiation covers a broad spectrum of phenomena, but in the context of space, we are mainly concerned with two types: electromagnetic radiation and particle radiation. Electromagnetic radiation is energy traveling in waves. Visible light is electromagnetic radiation. So are radio waves, microwaves, infrared light, ultraviolet light, X-rays, and gamma rays. These are all the same fundamental phenomenon, just at different wavelengths and energies. The lower energy forms, like radio waves and visible light, are mostly harmless. You are bathed in them constantly. But as you move up the energy spectrum toward ultraviolet, X-rays, and gamma rays, the radiation becomes increasingly dangerous because it carries enough energy to knock electrons off atoms. This process is called ionization, and radiation that can cause it is called ionizing radiation. When a photon of ionizing radiation passes through biological tissue, it strips electrons from the atoms in that tissue. This doesn't sound like much, but it is devastating at the molecular level. Atoms that lose electrons become ions, which are chemically reactive in ways they weren't before. These newly created ions can break chemical bonds, disrupt molecules, and trigger chain reactions of chemical damage. The molecules most vulnerable to this damage are the large, complex molecules that your cells depend on: proteins, lipids, and most critically, DNA. Particle radiation is different from electromagnetic radiation, but in many ways even more dangerous. Instead of waves of energy, particle radiation consists of actual physical particles, subatomic fragments moving at enormous speeds. These include protons, neutrons, electrons, alpha particles, which are helium nuclei, and heavy ions, which are the nuclei of heavier atoms like iron, silicon, or carbon stripped of their electrons and accelerated to tremendous velocities. In space, these particles come from two main sources: the Sun and the rest of the galaxy. The Sun constantly emits a stream of charged particles called the solar wind. This is a continuous flow of mostly protons and electrons moving outward from the Sun at speeds of about 300 to 800 kilometers per second. Under normal conditions, the solar wind is relatively low energy. It's more of a breeze than a storm. Earth's magnetic field deflects most of it harmlessly around the planet, and what little reaches the upper atmosphere produces phenomena like the aurora borealis, the northern lights. But the Sun is not always calm. Periodically, it produces solar flares and coronal mass ejections. A solar flare is a sudden, intense burst of electromagnetic radiation from the Sun's surface, usually associated with sunspots, regions where the Sun's magnetic field is particularly tangled and unstable. A coronal mass ejection is something different and potentially far more dangerous. It is a massive eruption of plasma and magnetic field from the Sun's corona, its outer atmosphere. A coronal mass ejection can release billions of tons of charged particles into space, traveling at speeds up to 3,000 kilometers per second. When these particles hit Earth's magnetic field, they compress and distort it, causing geomagnetic storms that can disrupt power grids and satellite communications. But here on the ground, you remain largely protected. In space, outside the magnetic field, it is a completely different story. An astronaut caught in a major solar particle event without adequate shielding would receive a potentially lethal dose of radiation in a matter of hours. The particles would pass through the walls of a spacecraft, through a spacesuit, and through the astronaut's body, ionizing atoms along the way and leaving a trail of molecular destruction. During the Apollo program, this was one of NASA's greatest fears. The Apollo missions sent astronauts beyond the protection of Earth's magnetic field for the first time. If a major solar particle event had occurred while astronauts were on the lunar surface or in transit between Earth and the Moon, the consequences could have been catastrophic. The spacecraft walls and spacesuits provided some shielding, but not nearly enough to stop a major solar storm. The Apollo astronauts were, in a very real sense, lucky. Several significant solar events occurred during the Apollo era, but none happened while astronauts were in the most vulnerable phases of their missions. One of the most intense solar particle events ever recorded occurred in August 1972, between the Apollo 16 and Apollo 17 missions. Had astronauts been on the Moon or in transit during that event, they could have received radiation doses high enough to cause acute radiation sickness, potentially fatal levels without immediate medical intervention. The timing was pure luck. A few months earlier or later, and the history of space exploration might include a very different and much more tragic chapter. The second source of particle radiation in space is far more constant and in some ways more insidious. It comes not from our sun, but from the rest of the galaxy and beyond. These are called galactic cosmic rays, and they are among the most energetic particles in the known universe. Galactic cosmic rays are atomic nuclei, atoms stripped of all their electrons, that have been accelerated to nearly the speed of light by some of the most violent events in the cosmos. Supernova explosions, the collapse of massive stars, the energetic jets produced by black holes, and other extreme astrophysical processes. These particles have been traveling through space for millions of years, bouncing off magnetic fields and gaining energy before they happen to encounter our solar system. Most galactic cosmic rays are protons, the nuclei of hydrogen atoms. About 12% are alpha particles, the nuclei of helium atoms, and roughly 1% are heavier nuclei, The nuclei of elements like carbon, oxygen, silicon, and iron. That 1% might sound insignificant, but these heavy ions are disproportionately dangerous. A single iron nucleus traveling at close to the speed of light carries an enormous amount of kinetic energy. When it passes through biological tissue, it doesn't just ionize a few atoms along its path. It ionizes thousands of atoms, leaving a dense trail of molecular destruction through the tissue, like a microscopic cannonball tearing through a building. This trail of damage is called a heavy ion track, and it can be devastating to cells. The DNA in cells along the track can be shattered, not just nicked or partially damaged, but broken in multiple places simultaneously. This type of damage, called clustered DNA damage, is extremely difficult for cells to repair. When a cell suffers simple damage to one strand of its DNA, it usually has repair mechanisms that can fix the break using the other strand as a template. But when both strands are broken in multiple places simultaneously, the repair machinery often fails. The cell may die, which is actually the safest outcome, or it may survive with errors in its genetic code, mutations that could potentially lead to cancer. On Earth, you are almost entirely shielded from galactic cosmic rays. The atmosphere above you is equivalent to about 10 meters of water in terms of shielding. That is a tremendous amount of material for particles to pass through. Most cosmic rays interact with atmospheric atoms long before they reach the ground. They collide with nitrogen and oxygen nuclei in the upper atmosphere, producing showers of secondary particles that are mostly absorbed before reaching the surface. The small amount of cosmic ray radiation that does reach sea level is a tiny fraction of what exists in space. Earth's magnetic field provides an additional layer of protection. Charged particles, which is what cosmic rays are deflected by magnetic fields. Earth's magnetic field acts like a giant invisible shield, bending the paths of incoming cosmic rays and deflecting many of them away from the planet entirely. The strongest protection is near the equator, where the magnetic field lines are roughly parallel to the surface. Near the poles, where the field lines converge and dip toward the surface, protection is weaker, which is why the auroras occur near the poles. Charged particles from the solar wind spiral along the magnetic field lines and enter the atmosphere near the magnetic poles, where they collide with atmospheric gases and produce light. In space, beyond Earth's magnetic field, there is no such protection. An astronaut on the International Space Station receives some protection because the station orbits within the magnetosphere, the region of space dominated by Earth's magnetic field. But even there, the radiation dose is significantly higher than on the ground. Astronauts on the ISS receive roughly 1 millisievert of radiation per day. On the ground, the average person receives about 3 millisieverts per year from all sources combined. So, an astronaut on the ISS receives in a single day what you receive in about 4 months. Over a 6-month mission, an astronaut accumulates a radiation dose roughly equivalent to what a ground-based person would receive in 60 years. And the ISS is still partially protected by Earth's magnetic field. Beyond the magnetosphere, in deep space, the exposure is even worse. Let me explain how radiation damages your body at the cellular level, because this is where the true danger lies. Your body contains roughly 37 trillion cells. Each of those cells contains a complete copy of your DNA, the molecule that carries the instructions for building and operating your body. Your DNA is a long, twisted ladder of chemical bases, about 3 billion base pairs per cell. If you stretched out all the DNA in a single cell, it would be about 2 meters long. If you stretched out all the DNA in your entire body, it would extend several times the diameter of the solar system. This DNA is not just sitting idle. It is constantly being read, copied, and used to produce the proteins that carry out virtually every function in your body. Enzymes that digest your food, antibodies that fight infection, structural proteins that build your bones and muscles, signaling molecules that coordinate your organs. All of these are produced according to instructions encoded in your DNA. When ionizing radiation passes through a cell, it can damage DNA in several ways. The simplest is a single-strand break, where one side of the DNA ladder is cut. These are relatively easy to repair because the other strand provides a template. Your cells repair thousands of single-strand breaks every day, just from normal metabolic processes. Double-strand breaks are far more serious. Both sides of the ladder are cut at or near the same location, leaving no intact template to guide repair. The cell has mechanisms for fixing these, but they are error-prone and sometimes introduce mutations. Other forms of damage include altered chemical bases and abnormal bonds between DNA and nearby proteins. All of these can lead to 3 possible outcomes. First, the cell repairs the damage correctly. This is what happens most of the time with low radiation levels. Second, the cell dies through a self-destruct mechanism called apoptosis, which is actually protective because it prevents damaged cells from dividing. Third, and most dangerously, the cell survives with unrepaired mutations. If those mutations affect genes controlling cell growth, the cell can begin dividing uncontrollably. This is cancer. A single cell in a single moment of radiation damage can become the seed of a tumor that might not appear for years or even decades. But radiation doesn't just damage DNA directly. It also damages tissue through an indirect mechanism involving water. Your body is about 60% water. When ionizing radiation passes through tissue, much of it interacts with water molecules rather than DNA. When a high-energy particle or photon ionizes a water molecule, it breaks it apart into highly reactive fragments called free radicals. The most dangerous of these is the hydroxyl radical, an atom with an unpaired electron that will react with almost anything nearby, almost instantaneously. A hydroxyl radical can travel only a few nanometers, but in that distance it can encounter and damage DNA, proteins, or cell membranes. This indirect pathway actually accounts for roughly 2/3 of the biological damage caused by radiation. The radiation doesn't need to score a direct hit on DNA. It just needs to get close. A heavy ion passing through a cell creates a dense cloud of these free radicals along its track. A cylinder of chemical chaos extending several nanometers in every direction. The cell is attacked not just by the particle itself, but by the chemical storm it leaves in its wake. The effects of radiation on the human body depend on the dose received, how quickly it is received, and what type of radiation is involved. At low doses, the kind you receive from background radiation on Earth, the damage is minimal and your body's repair mechanisms handle it easily. You accumulate small amounts of damage over your lifetime, and this contributes to the baseline risk of cancer that everyone faces. At moderate doses, the risk of cancer increases significantly. Studies of the survivors of the atomic bombings of Hiroshima and Nagasaki, as well as studies of workers in nuclear industries and patients who received radiation therapy, have shown a clear dose-response relationship. More radiation means more cancer risk. There is no threshold below which radiation is completely safe. Even small doses carry some risk. The risk is just very small at low doses and increases as the dose goes up. At high doses, acute radiation syndrome occurs. This is a medical emergency. The symptoms depend on the dose but can include nausea, vomiting, diarrhea, skin burns, hair loss, immune system collapse, and death. Acute radiation syndrome has distinct phases. First comes a prodromal phase with nausea and vomiting, often within hours of exposure. Then there may be a latent phase where the person feels relatively well for days or weeks. Then the manifest illness phase, where the full effects appear. The bone marrow stops producing blood cells. The immune system collapses. The lining of the intestines breaks down, leading to severe infections and bleeding. At very high doses, the central nervous system is directly affected, leading to confusion, seizures, and death within hours or days. For an astronaut in deep space, a major solar particle event could deliver doses in the range that causes acute radiation syndrome, and there would be no hospital to go to, no bone marrow transplant available, no intensive care unit, just a spacecraft, a few crewmates, and an enormous distance from any medical facility on Earth. The treatment options in such a scenario would be extremely limited. The type of radiation matters enormously. Not all radiation is created equal in terms of biological damage. Gamma rays and X-rays, which are high-energy electromagnetic radiation, are what we call sparsely ionizing. They tend to deposit their energy in a diffuse pattern as they pass through tissue, creating isolated points of damage scattered throughout the cell. The damage is real but spread out, and the cell's repair mechanisms can often handle it. Heavy ions from galactic cosmic rays are different. They are densely ionizing. They deposit enormous amounts of energy along a very narrow track as they pass through tissue. The damage is concentrated, severe, and difficult to repair. A single heavy ion can cause dozens of double-strand DNA breaks in a single cell, along with extensive damage to proteins and membranes. The biological effectiveness of heavy ions is estimated to be 10 to 20 times higher than gamma rays for the same amount of deposited energy. This means that a given dose of heavy ion radiation causes 10 to 20 times more biological damage than the same dose of gamma rays, and heavy ions are a significant component of the galactic cosmic ray environment. This is a particular problem for long-duration space missions. The longer you spend in space, the more heavy ions pass through your body. On a 3-year round trip to Mars, which is the kind of mission NASA and other space agencies are planning, an astronaut would be exposed to a cumulative radiation dose that significantly increases their lifetime cancer risk. Current estimates suggest the cancer risk from radiation exposure on a Mars mission could be as high as 5 to 10% above baseline, depending on the shielding and the solar activity during the mission. That might not sound like a lot, but it is a substantial increase. It means that out of every 100 astronauts who go to Mars, 5 to 10 additional ones might develop cancer as a direct result of the radiation exposure. And that is on top of whatever cancer risk they already had from other factors. There is also growing evidence that space radiation affects more than just cancer risk. Studies on animals exposed to simulated space radiation using particle accelerators that can produce beams similar to galactic cosmic rays have shown effects on the brain. Mice exposed to heavy ion radiation show changes in brain structure, including reduced density of connections between neurons. They perform worse on tests of learning and memory. They show increased anxiety and reduced social interaction. The implications for human astronauts are troubling. If heavy ions can damage the brain structure of mice, they could potentially do the same to humans. Astronauts on long-duration missions might experience cognitive decline, mood changes, and impaired decision-making, exactly the things you cannot afford to lose when you are millions of miles from Earth, and your survival depends on making correct decisions. Shielding against space radiation is an enormous engineering challenge. For electromagnetic radiation like X-rays and gamma rays, dense materials like lead are effective shields. But for particle radiation, especially high-energy galactic cosmic rays, shielding is far more complicated. When a high-energy particle strikes a heavy atom in a shield, it doesn't simply stop. Instead, it can shatter the heavy atom's nucleus, producing a spray of secondary particles, including neutrons, protons, and lighter nuclear fragments. This process is called spallation, and the secondary particles it produces can be just as damaging as the original particle, sometimes more so because neutrons are particularly effective at causing biological damage and are very difficult to shield against. This means that adding more metal shielding to a spacecraft can actually make the radiation problem worse in some cases. The heavy atoms in the metal provide targets for spallation, generating showers of secondary particles inside the spacecraft. The ideal shielding material would be something made of light atoms, which are less likely to undergo spallation. Hydrogen is the best shield against galactic cosmic rays because its nucleus is just a single proton. There is nothing to shatter. Polyethylene, a common plastic that contains lots of hydrogen, is actually a better radiation shield than aluminum for galactic cosmic rays. Water is also a good shield because of its hydrogen content. Some spacecraft designs have proposed surrounding crew habitats with water tanks, using the water supply as both a resource and a radiation shield. But even with optimal shielding materials, you cannot completely stop galactic cosmic rays. The most energetic ones carry so much kinetic energy that they can pass through meters of material. To provide the same level of protection as Earth's atmosphere, you would need several meters of water or equivalent shielding surrounding the spacecraft. The mass this would add makes it impractical with current rocket technology. You simply cannot launch that much shielding material into space with any rocket that exists or is currently planned. So, astronauts on deep space missions will inevitably be exposed to radiation levels significantly higher than on Earth. The goal of shielding design is not to eliminate the exposure, but to reduce it to levels where the increased health risks are considered acceptable. What constitutes acceptable risk is itself a difficult question that involves not just science, but ethics and policy. There is something deeply unsettling about radiation as a space hazard. Unlike vacuum, which at least announces itself, you feel the pressure drop, you feel the air leaving, radiation gives you no warning whatsoever. A galactic cosmic ray heavy ion can pass through your brain, shattering DNA in dozens of cells along its path, and you will feel absolutely nothing. No pain, no sensation of any kind. The particle moves so fast, just below the speed of light, that it passes through your skull in less than a billionth of a second. By the time any nerve signal could even begin to form, the particle is long gone, already millions of miles away, continuing its journey through interstellar space as if you were never there. The damage it left behind, the broken DNA strands, the free radicals tearing through cellular machinery, all of this happens in silence, You cannot see it. You cannot feel it. You won't know it happened. The only evidence might appear years or decades later, when a cell that was damaged by that single particle finally transforms into a cancer, or it might never appear at all. The cell might repair the damage perfectly, or it might die through apoptosis, quietly removing itself from your body. You'll never know which particles caused damage and which didn't. You'll never know which cells were hit and which were spared. The entire process is invisible from beginning to end. This is what it means when we say space can kill without touching you. Radiation passes through the walls of spacecraft, through spacesuits, through skin, through bone, and into the most fundamental molecules of your body. It damages you at a level you cannot perceive, in ways your senses cannot detect, through mechanisms that may not manifest for years. There is no moment of impact, no sensation of harm, just silent, invisible particles doing silent, invisible damage. And in the deep void between planets, between stars, this rain of particles never stops. It has been falling since the first stars exploded billions of years ago. It fills the galaxy, fills the universe, fills every cubic centimeter of the space through which any astronaut must travel. You cannot outrun it. You cannot hide from it completely. You can only reduce your exposure and hope that your body's repair mechanisms can handle what gets through. Space is not just empty. It is quietly, invisibly hostile. And radiation is perhaps the purest expression of that hostility. An enemy with no form, no mass you can feel, no sound, no signal of any kind. Just energy and particles moving through the void, indifferent to whether they pass through empty space or through the cells of a living body. To the radiation, there is no difference. You are just more atoms in the way. Most people, when they imagine being exposed to space, picture themselves freezing. It is one of the most common assumptions about space, that it is cold, unimaginably, instantly, lethally cold. Movies reinforce this constantly. Characters exposed to vacuum turn blue. Ice crystals form on their skin within seconds. Their bodies become frozen solid almost immediately, preserved like specimens in some cosmic deep freeze. And in a way, this assumption seems logical. Space is dark. Space is empty. There's no sun warming your living room, no heater running, no fire crackling. Just infinite blackness stretching in every direction. Of course it must be cold. But here's the thing. That assumption, while not entirely wrong, is deeply misleading. The reality of temperature in space is far stranger, far more counterintuitive, and far more dangerous than simply being cold. Because the truth is, space is not cold in the way you think of cold. In fact, in a very real physical sense, space does not have a temperature at all, and understanding why requires you to rethink everything you know about heat, cold, and how temperature actually works. Let's start with the basics. What is temperature? On Earth, in your daily life, temperature is something you experience constantly and intuitively. You step outside on a winter morning, and the air feels cold. You put your hand near a fire and it feels hot. You touch a metal railing on a summer day and it burns your fingers. Temperature seems obvious. It seems like a simple property of the world around you. But what you are actually feeling is not temperature itself. You are feeling heat transfer. You are feeling energy moving from one object to another. When you touch a cold railing in winter, the railing is not injecting cold into your hand. Cold is not a substance. There is no such thing as cold particles or cold energy flowing into you. What is actually happening is the reverse. Heat energy is flowing out of your hand and into the railing. The railing is at a lower temperature than your skin, so thermal energy moves from your warmer hand to the cooler metal. Your nerves detect this outflow of energy and interpret it as the sensation of cold. This distinction matters enormously when you start thinking about space, because heat transfer, the movement of thermal energy from one object to another, requires a mechanism. On Earth, there are three mechanisms by which heat moves: conduction, convection, and radiation. Conduction is heat transfer through direct physical contact. When you touch a cold railing, heat moves from your hand into the metal through direct contact between the molecules of your skin and the molecules of the metal. Metal is a particularly good conductor, which is why a metal railing feels colder than a wooden surface at the same temperature. Convection is heat transfer through the movement of fluids, meaning liquids or gases. When you stand outside on a cold, windy day, the wind carries heat away from your body much faster than still air would. This is why wind chill exists. The air itself might be at a certain temperature, but the wind moves that cold air across your skin more quickly, increasing the rate of heat transfer. Convection is also how your home heating system works. A furnace heats air, and that warm air circulates through your house, carrying thermal energy with it. Radiation is heat transfer through electromagnetic waves. This is how the sun warms the Earth. Sunlight, which is electromagnetic radiation, travels across 93 million miles of space and deposits energy on everything it touches. You feel this directly when you step from shade into sunlight. The air temperature might be the same in both spots, but you feel warmer in the sun because your body is absorbing radiant energy directly from the sunlight. Every object with a temperature above absolute zero emits thermal radiation. You are radiating right now. Your body is emitting infrared radiation in all directions. The amount is small, but is real and measurable. Infrared cameras work by detecting this thermal radiation, which is how they can show you as a bright, warm shape against a cooler background. Now, here is the critical point. In space, two of these three heat transfer mechanisms essentially do not exist. There is no air in space, no gas, no fluid of any kind. This means there is no conduction and no convection. You cannot lose heat to the air around you because there is no air. You cannot be cooled by a breeze because there is no breeze. There are no molecules around you to carry your heat away through contact or fluid flow. The only way to gain or lose heat in space is through radiation. This single fact changes everything about how temperature works in the space environment. On Earth, when you step outside on a cold day, the air around you is at a low temperature and it rapidly pulls heat from your body through both conduction and convection. The air molecules contact your skin, absorb energy, and move away, replaced by more cold air molecules. This is incredibly efficient. Cold air can cool your body dangerously fast, which is why hypothermia is such a serious risk in cold weather. Frostbite can occur in minutes when wind chill is extreme. The air is an active participant in cooling you down. In space, none of this happens. Without air, without any medium to conduct or convect heat, the only way your body can lose thermal energy is by radiating it away as infrared light. And radiation is a much, much slower process than conduction or convection. Your body does radiate heat. At normal body temperature, roughly 37 degrees Celsius, you radiate about 100 watts of thermal energy. That is roughly the same as a bright, incandescent light bulb. But this energy radiates outward in all directions from your skin. It is not being concentrated or carried away by a medium. It is just slowly streaming off you as invisible infrared light. At this rate of heat loss, your body temperature would drop, but it would drop slowly. Not in seconds, not in minutes. Over the course of hours, you would gradually cool, but the process is nothing like the rapid freezing depicted in movies. You would die from vacuum exposure and oxygen deprivation long before hypothermia became a serious problem. This is one of the most counterintuitive facts about space. You would not freeze quickly. In fact, freezing might be one of the last things to happen to you. The vacuum kills first. The radiation damages you silently. But the cold? The cold takes its time. So if space is not the instant deep freeze that movies portray, what is the actual thermal environment like? The answer depends entirely on one thing: whether you are in sunlight or in shadow. In the vicinity of Earth's orbit, if you are in direct sunlight, the side of your body facing the sun would be bombarded by solar radiation. The sun delivers about 1,360 watts of energy per square meter at Earth distance. This is called the solar constant, and it is substantial. That much energy hitting your skin would heat you up, not cool you down. The sunlit side of your body could reach temperatures well above normal. Surfaces in space that are directly exposed to sunlight can reach temperatures of over 120 degrees Celsius, roughly 250 degrees Fahrenheit, depending on their color and reflectivity. Dark surfaces that absorb more sunlight heat up more. Light or reflective surfaces absorb less and stay cooler. Now turn around. The side of your body facing away from the sun, the shadow side, is radiating heat into the void, but receiving almost no energy in return. Deep space, the cosmic background, has a temperature of about 2.7 Kelvin, which is roughly negative 270 degrees Celsius or negative 454 degrees Fahrenheit. This is the residual heat from the Big Bang, the cosmic microwave background, radiation. It is barely above absolute zero. Your shadow side is radiating heat toward this near absolute zero background and receiving almost nothing back. Over time, if you were somehow kept alive long enough, the shadow side of your body would cool dramatically. So here is the bizarre reality of temperature in space. One side of you would be roasting, while the other side would be slowly freezing. The thermal gradient across your body could be enormous. On the International Space Station, the difference between the sunlit side and the shadow side of the station's exterior can approach 300 degrees Celsius. That is roughly 500 degrees Fahrenheit of temperature difference between surfaces that might be only meters apart. There is no wind to mix the temperatures, no air to create equilibrium. Each surface is thermally isolated, interacting with its environment only through radiation. Astronauts on spacewalks deal with this directly. The sunlit side of a spacesuit can get extremely hot while the shadow side gets extremely cold. Spacesuits are designed with multiple layers of thermal insulation and reflective coatings to manage these extremes. The outer layer of an extravehicular activity suit is white and reflective to minimize solar heating. Beneath that are layers of insulating material to slow heat transfer. And the suit's life support system includes an active thermal control system that circulates water through tubes in the garment to carry excess heat away from the astronaut's body and distribute it more evenly. This thermal management is one of the most critical and least appreciated aspects of spacesuit and spacecraft design. In the vacuum of space, getting rid of excess heat is actually a bigger engineering challenge than staying warm. This might seem backwards. How can overheating be a problem in the cold void of space? The answer goes back to the fact that radiation is the only way to shed heat. On Earth, if a machine or a building generates excess heat, you can cool it with fans, with air conditioning, with water cooling. All of these rely on convection, on moving a fluid past the hot surface to carry the heat away. In space, you cannot do this on the exterior of a spacecraft because there is no external fluid to move. You have to convert the excess heat into thermal radiation and radiate it away into space. This is what the large radiator panels on the International Space Station do. Those big flat panels that extend from the station's truss are not solar panels. The solar panels are a different set of structures. The radiator panels are specifically designed to dump waste heat. The station's systems, the computers, the life support equipment, the experiments, the bodies of the astronauts themselves all generate heat. That heat is collected by a system of circulating fluid loops inside the station and carried to the radiator panels, where it is radiated into space as infrared energy. If these radiators failed, the station would overheat. The interior temperature would rise steadily because the heat generated inside has no other way to escape. The astronauts would be cooked not by the sun, but by their own body heat and the heat from their equipment, trapped inside an insulated box with no way to dissipate it. This has actually come close to happening. On several occasions, cooling system malfunctions on the ISS have required emergency spacewalks to repair or replace pumps in the external thermal control system. These are not minor maintenance tasks. They are critical repairs to prevent the station from becoming uninhabitable due to overheating. The lesson here is important. In space, heat management is about balance. You need to retain enough heat to keep the crew warm, but also shed enough heat to prevent overheating. And you have to do all of this using radiation alone, which is inherently slow and inefficient compared to convective cooling. This thermal balancing act is one of the fundamental engineering challenges of spaceflight. Every spacecraft ever designed has had to solve it, and every spacecraft that failed to solve it would have become either an oven or a freezer for its occupants. Let's talk about what actually happens to the human body in the thermal environment of space, because the physics creates some genuinely strange effects. We already discussed how water behaves in a vacuum. The boiling point drops so low that body temperature water vaporizes. This evaporation has thermal consequences. When water evaporates from the surface of your skin in a vacuum, it carries energy with it. This is the latent heat of vaporization. Every gram of water that vaporizes from your skin takes with it about 2,260 joules of energy. This is a lot of energy being removed from a small area. The result is rapid cooling of the skin surface. This evaporative cooling would actually be the fastest temperature change your body experiences in the first moments of vacuum exposure. Not the slow radiative cooling toward deep space, not the gradual loss of heat through infrared emission, but the rapid, intense cooling caused by your own bodily fluids boiling off your skin. The moisture on the surface of your eyes, the saliva in your mouth, the sweat on your skin, all of it would vaporize, and in doing so would chill the tissue beneath. This could produce localized frostbite-like injuries on moist surfaces, particularly the eyes, tongue, and nasal passages. But this is a surface effect. The interior of your body is insulated by layers of tissue, fat, and muscle. Your core temperature would not drop rapidly because the thermal energy has to work its way outward through layers of relatively poor thermal conductors. Human tissue has a thermal conductivity similar to water, which is much lower than metals. Your body is actually a fairly decent thermos, keeping its internal heat contained even when the surface is cooling. This means that even in a vacuum, even with evaporative cooling occurring on your skin, your core body temperature would remain near normal for several minutes. The outside of your body might cool significantly, especially in areas with thin tissue coverage like your fingers, toes, ears, and nose, but your heart, brain, liver, and other core organs would stay warm for a surprisingly long time. The thermal environment becomes even more complex when you consider the difference between orbital space near Earth and deep space, far from any star. Near Earth, in low orbit where the ISS flies, you are relatively close to a major heat source, the Sun, and also to Earth itself, which radiates a significant amount of thermal energy. The Earth absorbs sunlight and re-emits it as infrared radiation. Spacecraft in low Earth orbit actually receive substantial thermal energy from Earth's infrared emission, especially when passing over the sunlit side of the planet. This is called Earth albedo and Earth infrared. Radiation and spacecraft thermal engineers must account for it in their designs. The thermal environment in low Earth orbit is therefore relatively moderate compared to deep space. You cycle between sunlight and shadow every 90 minutes as you orbit the planet, and you receive heat from both the Sun and the Earth. In deep space, far from any planet or star, the thermal environment is much more extreme. The only significant heat source is the Sun, and its intensity decreases with the square of the distance. At Mars orbit, about 1.5 times farther from the Sun than Earth, solar intensity drops to less than half of what it is at Earth. At Jupiter, about 5 times Earth distance, it drops to about 4%. At Saturn, about 1%. By the time you reach the outer solar system, solar heating becomes negligible and the background temperature of space approaches that cosmic microwave background of 2.7 Kelvin. Spacecraft heading to the outer solar system face the opposite thermal challenge from those in low Earth orbit. Instead of managing excess heat, they must conserve heat. The Voyager spacecraft, now more than 15 billion miles from the Sun, rely on radioisotope thermoelectric generators, not just for electrical power, but also for waste heat, to keep their electronics from freezing. These generators use the decay of plutonium-238 to produce both electricity and heat. Without this internal heat source, the spacecraft's electronics would cool to temperatures at which they could no longer function. Even with the generators, some instruments on the Voyagers have had to be shut down over the decades as the plutonium decays and produces less heat and power. There is another thermal effect that astronauts encounter which most people never think about: the behavior of heat in the absence of gravity. On Earth, warm air rises because it is less dense than cold air. This creates convection currents that naturally circulate air in a room, carrying heat upward and drawing cooler air downward. This passive mixing helps regulate temperature naturally. You don't need a fan to prevent a room from developing extreme temperature variations, because natural convection keeps the air mixing. In microgravity, there is no natural convection. Warm air does not rise because there is no up. Hot air stays wherever it is. Cold air stays wherever it is. Without active ventilation systems, air around an astronaut's body would form a warm, stagnant layer, heated by body heat and exhalation, the carbon dioxide an astronaut exhales would accumulate around their head because it would not drift away naturally. An astronaut sleeping without ventilation could actually suffocate in a bubble of their own exhaled carbon dioxide. This is why the ISS has fans running constantly. The ventilation system is not optional, it is essential for survival. Without it, the air inside the station would stratify into pockets of warm and cold, pockets of oxygen-rich and oxygen-depleted air, creating a patchwork of habitable and dangerous zones within the same room. The fans keep the air mixed, distribute heat evenly, and ensure fresh oxygenated air reaches every part of the station. This is one of those dangers that seems almost absurdly mundane compared to vacuum and radiation. You could be killed by your own breath simply because warm air doesn't rise in zero gravity. But it is a real danger, one that the engineers who designed life support systems for spacecraft had to solve. And it connects back to the fundamental theme of thermal behavior in space. Without the familiar mechanisms of convection and conduction, heat behaves in ways that are deeply unfamiliar and potentially lethal. Let's also consider what happens to materials in the thermal environment of space, because this affects spacecraft, spacesuits, and any equipment humans use. On Earth, materials experience relatively modest temperature ranges. A steel bridge might experience temperatures from -40 to +50 degrees Celsius over the course of a year. That is a range of about 90 degrees. Engineering materials are designed to handle this range without problems. In space, the temperature range is vastly larger. Materials on the exterior of the ISS experience temperatures ranging from roughly -157 degrees Celsius in shadow to +121 degrees Celsius in direct sunlight. That is a range of nearly 280 degrees Celsius, more than 3 times the range experienced by materials on Earth. And this cycling happens every 90 minutes as the station orbits from shadow to sunlight and back. This thermal cycling creates enormous stress in materials. When a material heats up, it expands. When it cools, it contracts. Repeated expansion and contraction create fatigue in the material, weakening it over time. This is similar to how bending a paperclip back and forth repeatedly will eventually cause it to break. The metal doesn't fail on the first bend or the 10th, but after enough cycles, it fractures. Spacecraft materials experience thousands upon thousands of these thermal cycles over the lifetime of a mission. The ISS orbits Earth roughly 16 times per day. Over a year, that is about 5,840 thermal cycles. Over the station's lifetime of more than 25 years, that is over 146,000 cycles. Every bolt, every panel, every seal, every window has been heated and cooled over 100,000 times. The materials and joints must be engineered to withstand this relentless cycling without cracking, warping, or losing their seal. If a seal fails, if a microcrack develops in a window or a hull panel, the result could be a slow air leak or a catastrophic decompression. This is another way the thermal environment of space threatens human life, not directly, not by freezing you or cooking you, but by slowly degrading the structures that protect you. The spacecraft that keeps you alive is under constant thermal assault. Not dramatic, not violent, but relentless and cumulative. The extreme temperature differences in space can also cause a phenomenon called thermal shock. If a material is heated rapidly on one side while the other side remains cold, the differential expansion can cause immediate cracking. Glass is particularly vulnerable to thermal shock. On Earth, you may have experienced this by pouring boiling water into a cold glass and watching it crack. In space, thermal shock is a concern for optical systems, windows, and any component that might transition rapidly between sunlight and shadow. Spacecraft windows are made from specialized materials and designed with multiple panes and coatings to manage thermal stress. All of this, the radiative-only heat transfer, the extreme temperature gradients, the thermal cycling, the absence of convection, comes down to a simple but profound fact. Temperature in space does not behave the way your intuition tells you it should. Your experience on Earth, all the things you know about hot and cold, are shaped by living in an atmosphere. You live in a world where air carries heat, where wind cools you, where shade and shelter change the temperature around you in predictable ways. In space, all of those familiar rules break down. There is no air to be hot or cold. There is no wind to carry heat. Shade and sunlight create temperature differences of hundreds of degrees within inches of each other. Heat accumulates where you don't expect it and drains away by an unfamiliar mechanism. The thermal environment is not simply extreme, it is alien. And that alienness is what makes it dangerous. Because humans have no evolved instinct for managing heat in a radiative-only environment. We have no biological mechanisms for handling 300-degree temperature gradients across the width of our bodies. We have no innate understanding of a world where warm air doesn't rise, where you can overheat in the void of space, where your own breath can suffocate you because it won't drift away from your face. Every thermal danger in space is a consequence of being in an environment our bodies were never designed for. Just like vacuum kills through the absence of pressure, the thermal environment of space threatens through the absence of the thermal regulation mechanisms we evolved with. On Earth, the atmosphere acts as a thermal buffer. It moderates temperature extremes, it distributes heat, it creates the convection currents that mix warm and cool air. It provides the medium through which conduction and convection carry energy from place to place. Remove that atmosphere, and the familiar thermal world disappears entirely. The implications for long-duration spaceflight are significant. Every crewed spacecraft must carry its own thermal management system. Not just insulation, not just heaters, but an active, carefully balanced system that collects heat from where it is generated, distributes it where it is needed, and dumps the excess into space through radiators. If any component of the system fails, the consequences can be dire. Too much heat and the crew overheats. Too little and equipment freezes. An imbalance and some areas become too hot while others become dangerously cold. The thermal control system is as critical to survival as the air supply. Without it, the spacecraft becomes uninhabitable just as surely as if the hull were breached. And yet, thermal control rarely receives the attention that other systems get. Air supply, water recycling, radiation shielding. These are the systems people think of when they imagine the challenges of spaceflight. But thermal control is the silent partner that makes everything else possible. Without it, the electronics that run life support overheat and fail. Without it, the water in the pipes freezes and cracks the plumbing. Without it, the batteries that store solar energy become too cold to deliver power. Temperature is woven into every system on a spacecraft. It affects everything. And managing it in a vacuum, using radiation alone, with temperature swings of hundreds of degrees every 90 minutes, it's one of the greatest ongoing engineering achievements of the space age. Most people never think about it because it works so well. But every hour of every day that astronauts live and work on the International Space Station, they are alive because a thermal control system is quietly balancing heat, keeping the interior at a comfortable 21 to 24 degrees Celsius, while the exterior alternates between extreme heat and extreme cold just inches away on the other side of the hull. The illusion of normalcy, of comfortable shirt-sleeve conditions inside the station, masks the extraordinary thermal battle being fought constantly just beyond the walls. Space is not simply cold, space is thermally ruthless. It is an environment where heat behaves by unfamiliar rules, where familiar protections do not exist, and where the only barrier between a comfortable environment and a lethal one is continuous active engineering. The temperature of space will not kill you instantly the way vacuum will, but given time, given the failure of the systems that manage it, the thermal environment of space is every bit as lethal, just slower, quieter, and far stranger than you ever imagined. So far, we've talked about the invisible forces that make space lethal. The vacuum that causes your body to destroy itself from within. The radiation that shreds your DNA without any sensation whatsoever. The thermal environment that defies every instinct you have about hot and cold. Each of these dangers shares a common characteristic. None of them require anything to physically strike you. They are environmental conditions, properties of the void itself, that damage or kill simply by being what they are. But space has one more category of danger that bridges the gap between the invisible and the physical. And while it involves actual objects, actual particles of matter moving through space, the threat they pose is so far removed from our everyday understanding of impact and collision that it belongs in this same conversation about invisible lethality. Because in space, you can be killed by something so small you could never see it, moving so fast you could never react to it, striking with an energy that seems impossible for something of its size. And the line between particle radiation and physical debris becomes so blurred that the distinction almost stops mattering. What matters is the damage, and the damage is extraordinary. Let's start with micrometeoroids, because these are among the most persistent physical threats in the space environment. A micrometeoroid is exactly what it sounds like. A tiny meteoroid. Most of them are smaller than a grain of sand. Many are smaller than a grain of dust. They are fragments of comets, remnants of asteroid collisions, debris from the formation of the solar system 4.5 billion years ago. They drift through space in enormous numbers, and they have been doing so for longer than Earth has existed. On any given day, Earth sweeps up roughly 100 tons of this material as it orbits the Sun. Most of it burns up harmlessly in the upper atmosphere. Those streaks of light you see during a meteor shower are caused by particles often no larger than a grain of rice, vaporizing from the friction of atmospheric entry at speeds of tens of kilometers per second. The atmosphere protects us so completely that we experience these potentially lethal impacts as something beautiful, as shooting stars, as wishes made on falling lights. In space, there is no atmosphere to vaporize these particles before they reach you. A micrometeoroid that would have been destroyed 100 kilometers above your head on Earth will, in orbit, hit whatever is in its path at its full velocity. And those velocities are staggering. Micrometeoroids in low Earth orbit travel at average speeds of roughly 10 to 20 kilometers per second relative to a spacecraft. Some travel much faster. The fastest can exceed 72 kilometers per second, which is over 160,000 miles per hour. To put this in perspective, a bullet fired from a high-powered rifle travels at roughly 1 kilometer per second. A micrometeoroid at 20 kilometers per second is moving 20 times faster than a bullet. At 72 kilometers per second, it is moving 72 times faster. The kinetic energy of an object increases with the square of its velocity. This means that doubling the speed doesn't just double the energy, it quadruples it. An object moving 20 times faster than a bullet carries 400 times the kinetic energy per unit of mass. An object moving 72 times faster carries over 5,000 times the energy. A particle, the size of a grain of sand, traveling at 20 kilometers per second, carries roughly the same kinetic energy as a bullet fired from a handgun. That is enough energy to punch through multiple layers of aluminum. That is enough energy to penetrate a spacesuit. That is enough energy to kill. And you would never see it coming. At 20 kilometers per second, a particle crosses the distance of a football field in about 5 milliseconds. That is faster than a human nerve impulse can travel from your finger to your brain. By the time light reflected from the particle reached your eye, by the time your retina converted that light into a neural signal, by the time that signal traveled along your optic nerve to your visual cortex, by the time your brain even began to process what it was seeing, the particle would have already hit you, passed through whatever it struck, and continued on its way. There would be no warning, no sound, because there is no air to carry sound waves, no flash, visible to the naked eye because the particle is too small. Just an instantaneous transfer of energy from a speck of ancient cometary debris into whatever surface it happened to strike. The engineering response to this threat is called a Whipple shield, named after the American astronomer Fred Whipple, who proposed the concept in the 1940s. A Whipple shield is deceptively simple in concept, but elegant in execution. Instead of using a single thick wall to stop a micrometeoroid, you use 2 or more thin walls separated by a gap. The first wall, called the bumper, is relatively thin. When a high-velocity micrometeoroid hits the bumper, the enormous energy of the impact doesn't just make a hole, it vaporizes both the particle and the section of the bumper it hit. The solid particle is converted into a cloud of vapor and tiny fragments that expands rapidly as it crosses the gap between the bumper and the inner wall. By the time this cloud reaches the inner wall, its energy is spread across a much larger area. Instead of a single concentrated impact, the inner wall receives a diffuse spray of energy that it can absorb without being penetrated. The International Space Station uses Whipple shield configurations on its most vulnerable surfaces. Some sections have additional layers, stuffed Whipple shields that include blankets of ceramic fabric or other energy-absorbing materials between the outer bumper and the inner wall. These enhanced shields can stop particles up to about 1 centimeter in diameter, traveling at typical orbital velocities. That might not sound like much, but remember that the vast majority of micrometeoroids are far smaller than 1 centimeter. The shields are designed to handle the most statistically likely impacts. But no shield can stop everything. Larger debris, objects bigger than about 10 centimeters, can be tracked by radar from the ground. The United States Space Surveillance Network tracks over 27,000 pieces of orbital debris larger than 10 centimeters. When a tracked object is projected to pass close to the ISS, The station can perform a debris avoidance maneuver, using its thrusters to shift its orbit slightly and avoid the potential collision. This has happened dozens of times since the station became operational, but there is a gap. Objects between 1 and 10 centimeters in diameter are too small to track reliably from the ground, but large enough to penetrate the station's Whipple shields. These objects are the most dangerous because they cannot be avoided and they cannot be stopped. If one of them hit a critical section of the station, it could cause a catastrophic breach. The probability of such an impact on any given day is extremely low. But over the lifetime of a long-duration mission, the cumulative probability becomes significant enough that it is a real concern for mission planners. Orbital debris is different from natural micrometeoroids in an important way. Micrometeoroids are ancient, remnants of the solar system's formation. Orbital debris is human-made, the accumulated junk of 6 decades of spaceflight. Spent rocket stages, dead satellites, fragments from collisions, flecks of paint, bolts and screws. There are estimated to be more than 100 million pieces smaller than 1 centimeter in orbit. Roughly 500,000 pieces between 1 and 10 centimeters. And over 27,000 trackable pieces larger than 10 centimeters. The total mass is estimated at over 10,000 metric tons, and the problem is getting worse. Every collision creates more fragments, each of which can collide with other objects, creating still more. This cascading effect, predicted in 1978 by NASA scientist Donald Kessler, could eventually make low Earth orbit increasingly hazardous. In 2009, a defunct Russian satellite collided with an active American communications satellite, producing over 2,000 trackable fragments. In 2021, Russia deliberately destroyed one of its own satellites with an anti-satellite missile, creating over 1,500 trackable fragments and forcing the ISS crew to shelter in their docked capsules. The connection between micrometeoroid and debris impact and the other dangers we have discussed is deeper than it might first appear. A hull breach caused by an impact is not just a structural problem, it is a vacuum exposure problem. If a particle penetrates the hull of a spacecraft, the pressurized air inside begins to rush out through the hole. The rate of decompression depends on the size of the hole. A tiny pinhole might cause a slow leak that takes hours or days to become critical. A larger breach could depressurize a module in minutes or even seconds. The crew's response depends on how quickly they detect the leak and how large it is. The ISS has multiple pressure sensors that can detect drops in cabin pressure. If a leak is detected, the crew follows a well-rehearsed procedure. They seal off sections of the station by closing hatches between modules, isolating the leak to the smallest possible volume. Then, they search for the source of the leak, sometimes using ultrasonic detectors that can hear the high-frequency sound of air escaping through a small hole. In 2018, a small leak was discovered in the Soyuz MS-09 spacecraft, docked to the ISS. The leak was caused by a 2mm hole that appeared to have been drilled during manufacturing. The crew temporarily patched it with epoxy and gauze, while a more permanent repair was devised. The hole was small enough that the leak was slow, giving the crew time to respond. But the incident highlighted how vulnerable pressurized spacecraft are. A 2mm hole, smaller than the head of a nail, was enough to cause a measurable and potentially dangerous loss of cabin pressure. Now, Imagine a micrometeoroid impact creating a similar hole. The crew might not know where it came from or even that it happened until the pressure sensors detected the drop. But micrometeoroids and debris are not the only physical particles that threaten astronauts. There is another category of particle that we touched on when discussing radiation, but that deserves further attention in the context of physical impact. These are the charged particles, protons and heavy ions from galactic cosmic rays and solar events that we discussed earlier. We focused on their biological effects, on how they damage DNA and create free radicals. But these particles also interact with the physical structures of spacecraft in ways that create additional dangers. When a high-energy cosmic ray particle strikes the nucleus of an atom in a spacecraft hull, it can cause spallation, the shattering of that nucleus into fragments. These secondary particles, neutrons, protons, alpha particles, and heavier fragments spray outward from the impact point. Some of them travel deeper into the spacecraft structure. Some of them enter the crew cabin. These secondary particles can be just as biologically damaging as the original cosmic ray, sometimes more so. Neutrons are particularly problematic because they carry no electrical charge and therefore pass through a material that would stop charged particles. A shield designed to block protons might actually make the neutron environment worse by creating more neutrons through spallation. This is the fundamental challenge of radiation shielding in space. You are not just trying to stop particles, you are trying to stop them without creating equally dangerous secondary particles in the process. And for the most energetic galactic cosmic rays, particles with kinetic energies equivalent to a professionally pitched baseball compressed into a single subatomic particle, no practical amount of shielding can stop them entirely. They simply carry too much energy. They will pass through whatever you put in their way, and they will leave a trail of damage through every material they traverse, including human tissue. There is also an effect that charged particles have on electronics that poses an indirect but very real threat to crew safety. When a high-energy particle passes through a computer chip, it can ionize atoms in the silicon, creating a brief pulse of electrical current in the circuit. This is called a single event effect. If the pulse occurs in the right place at the right time, it can flip a bit in the computer's memory, changing a 0 to a 1 or vice versa. This is called a single event upset. Most single event upsets are harmless. A flipped bit in a data file might cause a minor error that goes unnoticed. But if the bit flip occurs in a critical system, in the flight computer, in the life support control system, in the navigation software, it could cause a malfunction. A command could be misinterpreted. A sensor reading could be corrupted. A control valve could open when it should close. Spacecraft. Computers are designed with redundancy and error correction to handle single event upsets. Critical systems typically use multiple redundant processors that vote on every calculation. If one processor gives a different answer from the other two, its answer is overruled. This triple modular redundancy protects against single-bit errors caused by radiation, but it adds complexity, weight, and cost, and it is not foolproof. Multiple simultaneous upsets, or upsets in the voting logic itself, could theoretically cause errors that slip through the redundancy. On the ISS, radiation-induced computer resets and anomalies are relatively common. They happen often enough that the crew and ground controllers have procedures for dealing with them. Most are minor inconveniences. But on a mission to Mars, where communication delays mean the crew cannot rely on real-time support from ground controllers, A radiation-induced computer malfunction could be far more serious. The crew would need to diagnose and fix the problem themselves in a spacecraft far from home, possibly while dealing with other radiation-related challenges simultaneously. All of this leads to a broader realization about the nature of protection in space. The barriers that keep astronauts alive, the hull of the spacecraft, the layers of the spacesuit, the radiation shielding, the thermal control system, the computer systems that manage everything, all of it is extraordinarily thin, extraordinarily fragile, and extraordinarily impressive at the same time. Consider the spacesuit. An extravehicular mobility unit, the suit used for spacewalks on the ISS, weighs about 127 kilograms. It consists of roughly 14 layers of material. The innermost layer is a comfort liner that sits against the astronaut's skin. Over that is a network of water-carrying tubes that form the liquid cooling and ventilation garment. Then comes a pressure bladder made of urethane-coated nylon that maintains the suit's internal pressure. Over the bladder is a restraint layer of woven dacron that prevents the bladder from ballooning outward under pressure. Then come multiple layers of aluminized mylar for thermal insulation, each separated by thin spacer fabrics. The outermost layer is a protective shell of orthofabric, a blend of Gore-Tex, Kevlar, and Nomex, chosen for its resistance to abrasion, tearing, and thermal extremes. This multi-layered system provides pressure containment, thermal regulation, micrometeoroid protection, and some radiation shielding all at once. And it works. Astronauts have performed hundreds of spacewalks in these suits over decades, spending thousands of cumulative hours in the vacuum of space. The suits have performed remarkably well, but they are not invulnerable. Every suit that has been retired from service and examined shows evidence of micrometeoroid impacts. Tiny craters and nicks in the outer layers where particles hit the suit and were stopped by the protective layers beneath. None of these impacts penetrate to the pressure bladder, but they serve as a reminder that the suit is constantly being bombarded. The outer layer is slowly being eroded by impacts too small to see and too fast to avoid. The suit survives not because it is impervious, but because the particles are usually small enough that the outer layers can absorb their energy before they reach the critical inner layers. The same is true of the spacecraft itself. The ISS has been in orbit since 1998. Over the course of more than 25 years, its exterior has accumulated thousands of micrometeoroid and debris impacts. Most are tiny, leaving craters a fraction of a millimeter across, but some are larger. In 2016, astronaut Tim Peake photographed a 7mm wide chip in one of the station's cupola windows, caused by a particle estimated to be only a few thousandths of a millimeter across, possibly a fleck of paint or a tiny metallic fragment. A few thousandths of a millimeter, smaller than the period at the end of a printed sentence, and it put a visible chip in a window made of fused silica and borosilicate glass designed to withstand the rigors of space. The cupola windows have 4 panes, precisely because of this risk. The outer pane takes the impacts, and if it is damaged badly enough, it can be replaced during a spacewalk. The inner panes provide redundancy, but the incident illustrates the relentless nature of the threat. Space is constantly throwing particles at everything in orbit. Most are harmless individually, but over time, the cumulative effect is erosion, degradation, weakening. The spacecraft ages not just from thermal cycling and radiation exposure, but from a continuous rain of microscopic projectiles that slowly wear away its surfaces. Now, let's connect all of this together, because the fundamental message of everything we have discussed tonight is not just that space is dangerous. Lots of environments are dangerous. The ocean is dangerous. Deserts are dangerous. The Arctic is dangerous. What makes space unique? What makes it unlike any other hostile environment humans have ever encountered? Is the nature of its hostility. Space is hostile through absence and through invisible forces. The vacuum kills through the absence of pressure. Radiation kills through invisible particles and waves passing through your body without any sensory warning. The thermal environment threatens through the absence of convective and conductive heat transfer. Micrometeoroids and debris threaten through particles too small to see and too fast to react to. None of these dangers announce themselves. None of them give you a chance to fight back, to duck, to run, to take cover in the way you might on Earth. On Earth, most dangers are visible or at least detectable. You can see a predator, you can hear a storm, you can feel extreme cold or heat, you can smell smoke. Your senses, the senses evolution gave you to survive in Earth's environment, are tuned to detect the dangers of Earth's environment. In space, your senses are useless. You cannot see the vacuum. You cannot hear the radiation. You cannot feel the micrometeoroid that just missed you. You cannot smell the charged particle that just passed through your cerebral cortex. Every danger in space is beyond the range of human perception. This is what makes space so fundamentally different from any other environment. It is not just hostile, it is imperceptibly hostile. It kills through mechanisms you cannot detect with any of the senses you possess. And this brings us to perhaps the most profound realization of all. The only reason humans survive in space is engineering. Not strength, not speed, not endurance, not any physical attribute that helps us survive in other hostile environments on Earth. Pure engineering. Mathematics, physics, materials science, chemistry, biology, all woven together into systems that replicate the conditions of Earth's surface inside a tiny bubble that we carry with us into the void. A spacecraft is not just a vehicle, it is a portable Earth. It provides the pressure your body needs, it filters the radiation that would destroy your cells. It manages the thermal environment that would otherwise either roast or freeze you. It shields you from particles you will never see. Every system on a spacecraft exists because without it, some invisible aspect of the space environment would kill the crew. The life support system replaces the atmosphere. The thermal control system replaces the weather. The hull replaces the magnetic field and the atmosphere's shielding function. The computer systems replace the ground-based infrastructure that supports human life on Earth. None of these systems can fail for long without consequences, and all of them are operating in an environment that is actively trying to degrade them. Radiation damages electronics. Thermal cycling stresses materials. Micrometeoroids erode surfaces. Atomic oxygen in low orbit corrodes exposed metals. The vacuum itself causes some materials to outgas, releasing trapped volatiles that can coat sensitive instruments or contaminate the cabin atmosphere. The spacecraft is under constant attack from an environment that cannot be negotiated with, cannot be tamed, and cannot be made safe. It can only be managed, moment by moment, system by system, with vigilance and redundancy and engineering that is just barely good enough to keep the people inside alive. When you look up at the night sky tonight, when you see the stars scattered across the darkness, remember what lies between you and them. Remember that the darkness is not just empty, It is actively hostile in ways your senses cannot detect. The vacuum is there, ready to pull the air from your lungs and the fluids from your tissues. The radiation is there, an invisible rain of particles traveling at nearly the speed of light, passing through everything in their path. The thermal extremes are there, hundreds of degrees of temperature difference between sunlight and shadow, and the micrometeoroids are there, ancient grains of dust carrying the energy of bullets, flying through the void on trajectories that have been unchanged for millions of years. All of this exists just above the thin shell of atmosphere that protects you right now. That atmosphere, that blanket of air stretching roughly 100 kilometers above your head, is the only thing separating you from an environment that would kill you in minutes through forces you would never see, never hear, and never feel. 100 kilometers. That is roughly the distance you could drive in an hour on a highway. If you could drive straight up, you would leave the protective atmosphere behind in 60 minutes. And beyond that boundary, everything changes. The pressure drops to nothing. The radiation levels skyrocket. The temperature swings become extreme. The micrometeoroids fly unimpeded. And every single thing that keeps you alive on the surface of this planet, the air, the pressure, the magnetic field, the thermal buffering of the atmosphere, all of it disappears. Space does not need to touch you to kill you. It does not need to send anything toward you. It does not need to act on you in any way you would recognize as an attack. It simply needs to be what it is: a vacuum, a radiation field, a thermal void, a shooting gallery of invisible particles, and your body, this extraordinary biological machine that evolved over hundreds of millions of years to function in one very specific environment, will fail. Not because it is weak. Your body is actually an astonishing piece of biological engineering. It can heal wounds, fight infections, adapt to changing temperatures, survive injuries that would destroy most machines. But it was designed for one world, for the pressure of one atmosphere, for the radiation levels filtered through one magnetic field and one atmosphere, for the temperature range moderated by one ocean and one air system. Take any of those away, and the machine begins to fail. Take all of them away at once, and it fails almost immediately. That is what space is. It is the absence of everything your body was built for. And in that absence, the very systems that keep you alive become the systems that destroy you. Your blood boils because the pressure is gone. Your cells mutate because the radiation shield is gone. Your thermal balance collapses because the atmosphere is gone. Space kills you with nothing. And nothing, as it turns out, is the most dangerous thing in the universe. We live at the bottom of an ocean of air on a small rocky planet orbiting an ordinary star. We are wrapped in a magnetic cocoon that deflects the worst of the cosmic radiation. We are warmed by convection and conduction through an atmosphere that moderates temperature extremes across the globe. We are shielded from micrometeoroids by 100 kilometers of gas that incinerates them before they ever reach us. All of these protections exist because of the particular circumstances of our planet. The right size to hold an atmosphere, the right distance from the sun for liquid water, the right composition in the core for a magnetic dynamo, the right everything really for life as we know it. And beyond this tiny shell of protection, the universe is waiting, patient, silent, invisible, and absolutely lethal. Space does not hate you. It does not want to kill you. It simply does not care whether you live or die. And its indifference, expressed through vacuum, radiation, thermal extremes, and microscopic projectiles moving faster than anything you could imagine, is the most dangerous thing you will never feel.